Hi, this is Anna Doblas with the second video of the module Fourier Optics for the course Intro to Optics and Photonics. The learning objective of this class is improving our understanding of propagation in Fourier space and understanding how the optical system or the free space optical system acts as a linear space invariant, define diffraction, recognize that there are three regions, the general one where we're going to have the Rayleigh-Sommerfield formula, the Fresnel and the Fraunhofer regions, and estimate the input response and the transfer function in free space. So let's assume that we have here a plane wave that it's illuminating a pupil and a picture, right? And if we have a plane wave, that means that the amplitude distribution is 1. But what we want to really see is what is the amplitude distribution just right before the pupil. So u sub t minus, that's gonna be my complex amplitude distribution right before the aperture or our pupil, and then this is gonna be equal to 1 if we have a plane wave illumination, right? And then we have our pupil. So we're gonna define here a pupil with a transmittant T of X. And what we have right after our pupil at any different plane, but just right after our pupil. So U sub T plus is gonna be the complex amplitude distribution right after the pupil, and the distribution that we have right after the pupil is gonna be what we have right before the pupil multiply the pupil transmittance. So remember that T, this is our pupil transmittance. And we definitely let to propagate the field. And if we are observing really far away, right, we are assuming that based on ray optics, we are saying that at any observation plane after any observation plane after the pupil, the amplitude distribution is our pupil transmittance. But we know that this is not true, right? This is what we are saying. This is what the ray optics will say, but we know that this is not true. What is happening is that in the case that we have a rectangular aperture, we're gonna have the diffraction patterns, right? And what we have is how we're gonna keep changing. And how we describe the diffraction pattern is with the Rayleigh-Sommerfield figure. Like we have different regions, but in particular, what we're gonna have is the Fresnel and the Fraunhofer. But what you can see here is that our aperture transmittance changes through the free propagation due to the diffraction. If diffraction does not occur, we always gonna have the same rectangular function. But because of diffraction occurs, we're gonna change the pattern. So when we have the Fresnel region, in this particular region, what we have is that the diffraction pattern change in shape and size. So in particular here, what we're gonna have is that our transmittance is gonna be convolved with the impulse response of the free propagation that we're gonna derive. We're gonna derive in this class the Rayleigh-Sommerfield, and then we're gonna do it, so the one for the Fresnel in the next class. Where now this distance C is gonna be the distance between the input and the output. In Fraunhofer region, what we have is just the diffraction patterns change in size, but we keep the same shape. So in Fraunhofer, the diffraction patterns are scale replicas of the two-dimensional Fourier transform. So that means if we have our pupil transmittance, then we're gonna have it. Sorry, let me try to be a little consistent with the colors here. For the Fraunhofer, we're gonna have its Fourier transform, 2D Fourier transform, where now the frequency is the x over lambda c, and then we have y over lambda c. So capital T is gonna be the Fourier transform of our space transmittance, where now our frequencies are x over lambda c. And you're gonna see that this has frequency dimension at b is gonna be y over lambda c. So basically the diffraction cause it's due to the light passing through the pupil deviate its original direction. And we know that the smaller the pupil and the aperture is, the more significant the diffraction is gonna be. And at the same time, if the distance that we are observing, if the separation between the input and output plane are farther away, it's higher, also the diffraction effects are gonna be more relevant. So when we are in Fourier optics, it's really important to identify where we have an aperture or a pupil or a mask, and then we always need to treat it as a independent. So we're gonna find what it's in front of. So we're gonna find what it's in front of right before the aperture, right? So we define the complex amplitude distribution before the pupil or the aperture, and then we know what is the transmittance of the aperture or the pupil. So we're gonna identify the complex amplitude distribution right after the aperture as the product of whatever we have before multiplied by the transmittance. And this is super important, and it's a key step in Fourier optics. When we are doing this step, our assumption is that the pupil thickness is almost zero. It's really thin. We don't have thick objects. So let's derive the Rayleigh-Sommerfield formula. So let's consider that we have two planes, our input placed at a distance c1 and our output plane placed at a distance c2, that they are far away, and we're gonna have two conditions. Let's first just pick a point here from our input, and it goes to our output, and then we're gonna define the distance between both planes. So the conditions that we have for the Rayleigh-Sommerfield formula is that the distance between the two planes is much larger than the source wavelength. The second condition is that each point within the input distribution U sub 1 emits a spherical wavefront. So that means that every point here is going to emit a spherical wavefront, and this is what we talk about it on the Huygens principle, and this is what it was key for module 2 when we were describing interference. So the absolute of the vector of R12, this is the distance between input and output planes. So if we want to, so everything right now is in 3D. So if we want to know the distance between with both planes, what we have is here the dimensions of this point. Let's say that this point is in alpha beta c1, and the point here at the output, that's gonna be x y c2. So we're gonna have that distance is x minus alpha squared plus y minus beta squared plus c2 minus c1 squared, everything square root. So now we can, for simplification, we can define the distance c12 like c2 minus c1. So we can define here c12 the square root of 1 plus x minus alpha over c12 squared plus y minus beta c12 squared. And when we want to estimate the complex amplitude in the output, what we're gonna have here is our integral in all the domain of the complex distribution in the output plane multiplied by c12 over j lambda, the distance between the two planes square, and then the exponential of jk r12. And now this is gonna be differential of alpha, differential of beta, and this integral we can try to put this like the c on the numerator is gonna cancel with one of the denominator. So we're gonna have here j lambda c, and here we're gonna have 1 plus x minus alpha c12 squared plus 1 minus beta c12 squared. We don't have now the square root because the square root cancels with the square in the denominator. And then on the numerator we have j k c12 square root of 1 plus x minus alpha c12 squared plus y minus beta c12 squared. And here we are missing the differential of alpha, differential of beta. Where I want you to see and pay attention is to this complex exponential here, because these are gonna be spherical. Those are gonna be represented by a spherical waveform. So our distribution sorry, I want the other marker. So the amplitude distribution in the output is a linear combination of spherical waveforms. So let's talk a little more about it. All right, so we have here our integral, right? And if you see our c value, the distance between the planes, it's a constant, right? So we have here, every time that we have x, we have x minus alpha or y minus beta. So this means that we can write this integral as a convolution. So the complex amplitude distribution in the output plane is the convolution of the input complex distribution convolved with 1 j lambda, the distance between the planes, 1 plus x squared plus y squared c12 squared. I'm just simplifying, and then here we have the complex exponential j k c12, the square root of 1 plus the same x squared plus y squared square root of c12 squared. So when we are talking about linear shift invariant systems, or the analogous, which is going to be linear time invariant systems, then we always define that the output distribution or the output signal is convolving the input with an input response. So that means that our input response of free space, right? Because the only thing that we are doing is we are ready to propagate the input. So the amplitude, the input response is gonna be this 1 over j k c12 1 plus x squared plus y squared c12 squared. And now here we have our exponential of j k c12 1 plus x squared plus y component, and then the distance squared. All right, so this term right here, this is gonna be our spherical waveform, while this term, but this term right here only affects the amplitude. So a lot of time we can ignore it. So we can say, just thinking about how it's gonna change the distribution, it's gonna be proportional to our spherical, our spherical pattern. And now if we do the Fourier transform, we're gonna estimate the transfer function, which is gonna be proportional to jk c12 1 minus lambda squared u squared plus v squared. So this is gonna be the transfer function of free space. Free space propagation. And if we want to do that means that the spectrum of our output is gonna be the product of the spectrum of our input combined with the transfer function. And this is one right. This one right here, this is gonna be our input spectrum. Alright, so we're gonna continue more with transfer function, the impulse in the Fresnel region in the next class. Thank you.